Yeah.
Hey, let's figure out, guys. The ones who don't speak, is there a way to mute the voice?
Yeah.
So we have the background off, and then when you speak, you unmute it.
Yeah.
I know. I have to get used to this. I'm not sure. Although I love hearing all the background. It just gets, it's wonderful. I get jealous when there's kids in the background. So make sure you turn it off in the background. All right, we have learned, let me see, I have to look at this in different angles here. We have learned before that muscle contract and actively shorten, that is the main activity they do all day long if required. How does the body use its quality? Choose all the time. Oh, look, I'm showing the answers. That's not what I want to do. Here we go. There we go. Oh, no, that's not good.
Really?
Let's see here. There we go. Maybe. So all of them are all right? You get that? Anybody?
Yeah.
Hold on.
I'm not sure I got it. I didn't think that through, but it all goes with the answers. Otherwise, let me see. Hold on. Let me do this. Let me see. Take the quiz. I don't want to change the quiz. I want to just take the quiz.
So it was pretty much everything except main posture, correct?
No, it's all of them.
Up.
Even the posture is all of them.
Okay.
Man, I knew it. I did all of them at first, and then I did like 4 different combinations, and I was like, "What's wrong?"
Well, it was my fault too because I didn't do it the right way, and then I got an email. I'm not sure. I think it was Chris who sent me an email. So it's basically all of this stuff. It does all of that. So if you think about it, muscle just contracts. That's all it does. And what does that help you with doing? It helps you, it attaches to bones. Muscles attach from bone to bone mostly, and then they contract. And so they hold bones closer together and put a tension on it. And so what can that help you with? Movement, posture, hold things together. Like if you think of the gut, it holds the soft tissue in. And then it can regulate movement in and out. If you think of eating, you need some muscle to be able to eat. And then shivering is generating heat. So they're all involved, basically. That makes sense?
Mm-hmm.
Yeah.
Let's go next one. When we look at how a muscle is built and consider what its quality are, we mentioned the fact that it contracts. It also needs to be able to receive information telling of when to contract. The brain mostly controls our skeletal muscles, the ones that make us move around. Can you list other muscle characteristics? Choose all that apply.
Elasticity, extensibility, and excitability.
Yes, and not stiffness or brittleness. We don't want those qualities in muscle. Those are the ones, when we get up in the morning, we're all stiff. We don't want that in muscle. We want the muscle to be flexible. So it actively contracts, and it passively has to be able to just relax and let go and extend. So that needs to be elastic. If it's brittle, as we get old, what I've noticed working on people's muscles, if people are well hydrated, they actually have soft muscles even in their 80s and 90s. If people are dehydrated a lot, their muscles get like beef jerky. And so that's more brittle, so they don't extend that as easily anymore. And so we also don't want that as a quality. So those are the 2 ones. Make sense?
Mm-hmm.
Right,
Yep.
Look, now we're online. I can have other people read for me. No, let me do the reading. How about that? Reading. Oh, and wait a minute. I want to go to the PowerPoint too and make sure we check on that. Those are the terms right there, right? And then we get to the reading and adding language is often confusing and difficult. It's like a foreign language. That is because a lot of the words used are constructions of Greek and Latin pre and suffixes. if you learn those, you will be able to understand that language much better. Name the 3 prefixes that describe muscles in here. Where are we? Oh, shoot. Hi, that's my old dog. Hello.
Oh.
I know. That was the last picture we took. That was the last picture before he went bye-bye.
He has a big nose.
Oh, yeah. He was old for his age. You see,
It's cute.
he came to work with me for 6 years. He was like, help me with all my anxieties. Yes, have a pet with your anxieties. It helps a lot. Anyway, there we go. What I know, I want them on again now. What are the 3 prefixes that describe muscle?
Mayo.
Mayo, good. Somebody's brave. Mayo.
Sarco.
Which one?
Sarco.
Sarco, very good.
Miss.
And MYS. All right, there you go. MYS. Also, I want to let you know, if you don't want, some people ask me privately, if you don't want the video showing to people, you just tap the audio only, all right? For that, make sure, just so you have your, you don't do this if you don't realize you're recording yourself. Oh my God. I've been having some wine and nobody noticed it, but
I've been having a beer and nobody noticed.
I know. I have my wine before the class, so.
Professor?
I tried to figure this whole thing out all night, so I'm like, I'm having a wine. Yes.
My wife's account signed off for some reason, but she's trying to get back on.
Okay. We'll be all right. All right, so those are the prefixes and those 3, like me, Mayo, Sarco, and Misio. So let's go to the next section here.
Okay.
Most of the time, oh, there we go. That's good, because one of the things I didn't want is have video, and I'm trying to make a YouTube video out of it. Most of the time, we think of muscle, we mean the ones that move us around in the world. We also have the other ones that we don't think of too much about, but they're equally important. There's 3 other types of muscles. Anybody?
Smooth, skeletal, and cardiac.
Good. Respiratory is a muscle itself. I mean, respiratory is a skeletal muscle. When you look at your right underneath your rib, you have a diaphragm. So when you breathe in, your stomach goes out, right? And so the diaphragm is right underneath the rib cage, and when it contracts, it sort of moves the ribs down, not the ribs, but it moves itself downward, and that pulls the lungs down, and that movement makes you inhale. And so that is a skeletal muscle. It's not here a skeletal muscle. That's a skeletal muscle itself. So that the respiratory sort of muscle is a skeletal muscle, and the intestinal muscle here is a smooth muscle, because all the tubes and the hollow things, the bags like a bladder in our body, they have skeletal. I mean, they have smooth muscles around them and in them, and they contract. But they're very different. The way they contract than skeletal muscle is on its own. Skeletal muscle, the one we're going to talk about most in here. And then cardiac muscle is just the heart muscle itself. And the heart muscle has, oh, my printer keeps going. And the cardiac muscle is the heart muscle, and that's only around the heart. And the big important thing there is the fact that the heart needs to contract. Well, first of all, it has to be unconscious. You don't want it to be conscious, so that's involuntary. Thank God, you don't have to think about it. But the other important thing about it is the whole heart has to contract as one unit, but it's not made of one muscle. It's many muscles that make up the whole heart. And so you have these intercalated discs in here, and they have gap junctions. And we learned in the third chapter or fourth chapter that we have junctions. We learned it in epithelial tissue. We have these junctions, and the gap junctions mean that ions, you see one here where there's the arrow, ions can move from one muscle cell to the next. And so that quality is very unique to the heart muscle, and it lets the heart contract as what they call a syncytial. And so that means it's a contraction all at once. And so that's very specific. So we'll talk about that when we get to the heart muscle a little bit more in detail. And so that was that answer there. So the intestinal muscle is one of the smooth muscles, which is described right up here. Does that make sense?
Yes.
Yeah.
A muscle mainly needs to contract. Yeah, speak up if you have a problem. It's like very weird to speak into my computer and have people listening. I've never known that before. So make sure you be part of the conversation. In order to know when to do that, a nerve communicates with it. Muscles have three main specific organelles that make the contraction possible. First, the cell membrane is specialized in that it can be stimulated by a nerve and carry an impulse deep into the muscle via tubular extensions. What is the cell membrane in a muscle called?
Sarcolemma.
Sarcolemma. Absolutely perfect right there. So that goes back then to here. The sarcolemma is the cell membrane that surrounds the muscle fiber. It can transmit an electrical impulse because it has to be stimulated by nerves in order to contract. So this description now, what we talk about now is all skeletal muscle. So skeletal muscle does not contract involuntarily. So that means the brain has to talk to it. And that's how when the nerve, and that's a nerve, it does that by a nerve. So have you ever hit your funny bone?
Oh yeah.
Yeah, so then you're like feeling the shooting going down your forearm. So that's
almost like electricity, isn't it?
Right, and that's that nerve impulse. Basically, you feel a nerve impulse at that point, and that's what goes to the muscle also when it needs to contract. And it goes from the brain to the muscle, and that makes it voluntary. That makes it like, well, it's the voluntary part of the brain for the most part, but that makes it like, hey, I want to go walk over there, and your brain talks to the muscles that make you walk over. So that's where it's interesting to understand, if you have to, let's say somebody has a stroke or somebody sometimes they have some limbs or some nerve severed that they can reattach, but sometimes they don't reattach them right. And then they have to relearn what goes to where from the brain. It's very complicated. But it's very interesting. So that's the sarcolemma right there. Let's see what's next here. That makes sense?
Mm-hmm.
Yeah.
Sarcolemma. No, wait. Technically, our muscles have long thread-like organelles that do the actual physical contraction. They lay parallel to one another and span the entire muscle length. What are the other specialized organelles called? What are those called?
Myofibril.
Which one?
Myofibril.
The myofibrils.
Myofibril.
Myofibrils. Actually, you probably go to Spain, they say myofibril, I think.
No.
So they're the shortening contractile organelles in the muscle cells. The myofibrils are arranged parallel to each other, the whole length of the muscle. So if you look at you feel your biceps in the front of your upper arm. You go all the way up to the shoulder. We talked about that now, right? That's the greater tubercle area in the humerus, and you can go all the way down to the radial tuberosity in the forearm. That's on the radius, and that whole length is the biceps brachii. That's the show-off muscle in the people, right? And one of these myofibrils is the whole length of that muscle. And when a muscle contracts, we're going to study the contraction within one of those myofibrils. So one of those myofibrils, so this is the whole bicep muscle. This is one of those strands, myofibrils. And then one of those units from like up and down line to up and down line, that's what we're going to describe and discuss when we discuss this. That's from one of these places here to one of these places here. All right? Does that make sense? So let's see where it takes us from there. So that's that thing. Those organelles are filled with two kinds of well-arranged protein threads. When a muscle contracts, one of them grabs the other one and pulls on it. Then you name the two kinds of protein threads. Actin and myosin. Perfect. Let's see. So when you look at this thing here, that whole thing is a section of one of those myofibrils, and inside there we have these threads, and this is one of these long thread-looking thing, and that's a thick filament, and that one of them looks like that. It has a tail, like a thread-like thing, and the head at the end, and the other one is a thin filament, and that's the actin. That looks like just a thread, and then at the end of the day is the place where we have this head attaches to this actin here. So the myosin head attaches to the actin at different places that are called active sites. And then what the head does, it does this motion right here that you can see. There's this backwards motion. And that, when many gazillions of these things are doing that, that's when we shorten a muscle, we contract the muscle. Because ultimately, these two ends of this part of the myofibril, which is actually called a sarcomere. See this word here, sarcomere? Those two ends then come together because because they are grabbing. See these lines here and these lines here are grabbing on this middle line here, and when they're pulling each other close this way, because this head goes like that, then they come, these Z lines, it's called Z lines because they're zigzags. Zigzag means Z. They come closer together, and that shortens a muscle. When you do that all the way through the length of this entire myofibril, your entire biceps or whatever muscle you look at, then you get the muscle contraction. Does that make sense?
Yeah.
A little bit? I know it's kind of the tough stuff. The physiology can be a little bit tough, but you want to have somewhat of a story in your mind, and make sure you ask questions, or even next class ask questions around it as we get through the stuff. All right, so that was that. Now we have the pulling action requires lots of energy, which is delivered in the form of ATP molecules. The fact that one can grab the other has to do with the presence of calcium. The third very important organelle is a bag-like structure similar to the endoplasmic reticulum. Remember from the cell chapter. You remember that?
Kind of.
A little bit. The endoplasmic reticulum. I know, right? It's a long time ago. And that so in a muscle, that ER stores the calcium ions versus being, a factory for protein and for lipid stuff. And so it has its special name. What is it called?
Sarcoplasmic Reticulum.
The Sarcoplasmic Reticulum, exactly. Perfect. So that, when I look at this slide, it's this blue stuff right here, this blue baggy thing. That's the Sarcoplasmic Reticulum. Let's see, where is there a thing? Yeah, see here, Sarcoplasmic Reticulum. Here we go. Go to these things. Now, during muscle contraction, a nerve stimulates the cell membrane, which sends a message to contract deep into the muscle cell or fiber. It activates the third organelle to release calcium, which then makes the pulling thread be able to grab the other one. The thicker thread has a kind of a hand or a head. They call it a head, which on one side and that bends back and forth. It's what grabs the thinner thread and pulls on it. That ATP molecule gives it the energy to pull. So that's why ATP is always the energy molecule. You always remember that. then it also makes it able to detach from the thinner thread to then grab again and pull some more. A little complicated, but kind of cool, right? That's basically how muscle contracts. That cycle is repeated a gazillion times, and voila, you start moving your limb. What is that cycle called?
Sliding filament theory.
The sliding filament theory. Good. The citric acid cycle is actually the cycle we use to make ATP. We don't have to go through that. You'll do that in a higher level biochemistry thing. So don't worry about that one. So that sliding filament theory is right here. What we're looking at really we described this thicker myosin filament, or the myosin molecule, and then the thin is the actin molecule. And that's right in here. That thing. The myosin is represented here with the head right here, and the actin is the blue one. And here you can see how here we can see. Let's go to the first one. So the first one is when the head is already in a high energy state, they call that, or configuration, and it attaches, the myosin head attaches to the actin molecule where there's an active site. And then on this one, the number 2, it's called the working stroke, where the head, it's like you think of a spring that is cocked. Here it's cocked and ready to go. And here you release it and it just bends backwards. And at that point, the ADP and the ATP, which is attached to it, we'll get to the ATP later, the ADP and the phosphate, detach, and the energy is released, and that spring is released, and it pulls, that myosin head pulls the actin a little closer to the midline of this, Z line on one side, Z line on the other, a little bit closer to that midline, and that contracts the muscle. And so then at that point, we have an ATP, which is the high energy molecule, comes back in, and the first thing it does, it detaches the head from the actin. So the myosin is detached from the actin. Then the second thing it does, it hydrolyzes. So what that means, the phosphate, the third phosphate, detaches from the ATP, and that gives you a lot of energy. And that basically recouples the spring to bring it into a high energy configuration. The whole cycle goes around and around and around. Does that make sense? Yeah? Anybody who got the background noise, you can slow it a little. That would be great.
Please.
I don't know who it is. I hope it's not me. I try to keep it down, but it's sometimes hard to notice when it's somebody. So try to think about it, because it's hard to concentrate when I talk. I hear all that stuff in the background. All right, so that was that sliding filament theory, and we could take it more when we talk about it. Actually, give me a second, because but I'm thinking it's pretty simple, and I can't. Oh, it's doing the same thing over and over. I'm sorry. All right, I'm back. Muscle cells contract when a nerve stimulates. You do that? No, when stimulated, they contract as strong as they can. The strength of a muscle contraction is determined by how many of the small thread-like muscle cells are stimulated by one nerve at one time. Nerves connect to great amounts of muscle fibers and activate them all at once when they fire. What do we call a nerve and all the muscle cells that it innervates?
Motor unit?
Anybody?
Motor unit?
Huh?
Motor unit.
There you go. Motor unit.
Motor
right
unit.
Down in here. Sorry. So, blah, 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 blah.
You can hear it, huh?
There you go. So what's important about this is that if you have a facial muscle, like you try to smile, and you compare that to trying to straighten out your knee when you kick a soccer ball, it's a much different force, right? So the facial muscle is a very little amount of force that is required to lift the corner of the mouth up, versus kicking a soccer ball that requires a lot of force. But when you look, so that's the more fine-tuned that a muscle contraction needs to be, the less one nerve, the less motor, the less muscle cells one nerve innervates. So in the facial muscle, when you just need to, which muscle is that? The zygomatic muscle that makes your corner of the mouth go up? You only have one nerve in the brain that connects to a very few amount of muscle cells. But in a quad, in a leg, when you need to straighten out the foot to kick a soccer ball, you don't need that much fine-tuning. Yeah, maybe the background noise is off. Or
Yeah,
if you don't
too
talk,
much.
the
I
noise,
can't concentrate with the noise.
I don't know, just anybody who's walking around, just make it on mute and then bring it back when you come back to being quiet. Then we're good. Because I need the feedback too for you guys, so I know I'm not talking into the. But the quad, you don't need as much fine control, so you can have one nerve innervate many more muscle cells, and you then have a much easier way to have the brain not be overloaded by having to fire so many nerves when you want to straighten out a quad. So if you would have, in other words, if you would have the same amount of muscles be innervated in the nerve innervation to the muscle cells in the quad as in the face, the brain would have to fire a huge amount of nerve going into the quads in order to make the contraction be so strong. Does that make sense?
Yes.
The more motor unit recruited at the same time, the stronger the muscle contraction. That's basically what I'm trying to say. All right. So, and what's important, the other thing that's important here is if a muscle is fired to contract, it does it best it can to just contract. It's like a machine. It's an on and off switch. It's not like, oh, we do a little bit. It does everything it can. All right. The muscle contraction uses a ton of ATP. Most of that is in a resting state. It's produced in the mitochondria, which a muscle has a lot of. However, if that is not enough, the muscle needs to be able to get energy from alternative sources. Remember, ATP becoming ADP as it gives off energy. Remember that?
Yeah.
We talked about that, right? That third phosphate from ATP, you split that third phosphate off. That's piece for phosphate. That's the energy ball, and then it becomes a diphosphate. So that's why it's another T for tri. In order to make ADP back to an ATP molecule, a phosphate has to be reattached. And there is a molecule in a muscle that has actually doing that. What is the molecule called?
Creatine phosphate.
The creatine phosphate. Yeah, good. So that is in this part of the chapter where we have the regular mitochondria that helps us a lot with ATP, but then we also have the creatine phosphate right in here. And if you go further into biochemistry, you go further into these details. But I think for us, the creatine phosphate one is the one I think is to kind of remember. Besides, you remember the mitochondria does the energy production in every cell, right? Remember that, right?
Yes.
Good. Some muscles are conserved with posture as they have to contract for long periods of time. Those muscles are also a little slower in contracting than others. The faster ones can react quickly. The fast ones can react quickly. They mainly are used to move us around. The composition of muscle is slightly different depending on what they are needed for. Postural muscle, for example, have more oxygen storage molecules that assure long sustained contraction. What are those called?
Oh, they can't hear you.
The myoglobin.
Perfect. Yeah, I'm looking right at it. The myoglobin right here. So that's like you think of like if you're standing up. I mean, if you did the posture, the more we slouch and when we stand, the more energy we use because the more muscles have to contract in order for us to hold us up. But muscle contraction uses a lot of ATP and energy. And so that's why if we have poor posture, we end up being more tired. And when we just have poor posture, we might not feel that. But if I have somebody coming in with a car accident, for example, and their muscles try to hold these joints together that have been, ripped from the face, then they are really, really tired. And so the muscle uses a lot of energy, and postural muscle in particular use a lot of energy. And wherever you use a lot of energy, you need a lot of oxygen. And the hemoglobin carries the oxygen around in the muscle. And in the muscle, we have this molecule called myoglobin. And that is like if you think of a hemoglobin being a magnet for oxygen, it picks up oxygen like it sucks it up. And if it goes to the tissue, it gives it away. If it travels by muscle, the myoglobin is a much stronger magnet, and it sucks all the oxygen off the hemoglobin. And so that is there specifically because muscle use so much ATP. All right? Make sense?
Yeah.
I don't know. I'm going less and less making sense, but less and less background noise too, so that's good. But make sure you ask questions, all right? Even though it's a little awkward here. And just speak in. Don't worry about interrupting me. That's cool. If you lift something off the ground, your arm muscle contract to raise the weight. When the muscle shorten during the contraction, we call it being an isotonic contraction. What do we call it when the muscle length doesn't change?
Isometric.
Isometric. Perfect. So when I look at those, have you heard of this isotonic isometric thing? Anybody? So when you go to the gym, they might talk about it. They might talk about eccentric or concentric exercises, contractions. Nobody? And let me enlighten you. So when you look at the word iso, the word iso means the same. Iso means the same. And an isotonic contraction, you're lifting something off the ground, for example. So your tone. No, wait a minute. Yeah, your tone of your muscles, the amount of muscles you contract, technically speaking, stays the same, but your length changes. When you look at an isometric contraction, the word meter, if you're coming from a metric world, not a world where you do about foot and miles, meter means length, right? Isometer. And so that means the length of the muscle does not change, it stays the same. So that means when you walk around with the grocery bags that are like heavy and you keep holding them in the same length, but you don't change the muscle length, you just try to get home. Have you ever had that? I'm sure, right? That's an isometric muscle contraction. When you take the grocery bag and you do curls and say, hey, honey, look at my forearms, I'm strong. That's an isotonic contraction. And then when you look at an isotonic contraction, so that would be making curls if you're doing curls. When you look at an isotonic contraction, when you bring the muscle up, contract the muscle, when you shorten the muscle, so when you curl it up, that's a shortening, that's a concentric contraction. And when you let it go to lengthen the muscle out, that's an eccentric contraction, that's the lengthening. And the funny thing is, when you go to the gym, you want to not just work on a concentric, which is you curl up and show everybody how thick and big your muscle is so you're looking cool. That is fine, but the eccentric contraction is where you actually build more muscle. So when you let a weight go, you want to let it go slowly and not just drop it down. Does that make sense?
Yeah.
Good.
Yeah.
Well, you know, I'm past 50 now, so I got to start doing muscle weight stuff. So I got to start being interested in that. All right, muscles come in many shapes. Oh, good. To accommodate the different forces put upon them. One of the interesting differences between certain muscles are the muscle fibers attached to a tendon, which then anchors it to the bone. Parallel arranged fibers are long with limited lifting strength. when the fiber attaches to a tendon in an angle, the individual muscle fibers are shorter, which gives them a greater lifting power. Those fibers kind of look like feathers. What do we call that arrangement?
Penne?
Penne.
Penne.
Penne. So it's kind of interesting that the feather-like is penne in that word pen. You know, in the old days, it was a feather, right, that we cut. So that's the penne. That's a bipennate here, multipennate here. But you see unipennate, that's the easiest one. So you see when you look at this muscle, when one fiber goes from here all the way down, that contracts. And then you got one like here where you have a longer tendon, which your tendon goes into the bone, right? And all these little fibers coming in from an angle, and then all they contract. That's a stronger contraction. Does that make sense? This compared to this? Okay, cool. Because it took me a while to understand it, but once I understood that, then it made more sense. Why do we have different muscle shapes? This one is also interesting. This is the rectus abdominis, the six-pack muscles in the front of your stomach. And it has these fibers. That's why we see the six-packs in here. These horizontal fibers that are like tendons themselves. So all these contract, these contract, these contract, and these contract all individually. So if the muscle as a whole contracts, you have like 3 muscles contract at the same time compared to this one here, which this is like a biceps type muscle. Anyway, I thought that when I learned that was kind of interesting. Oh, look at that. Good. Last question of this first section here. When a muscle contracts and shortens, they rub against other tissue. This can create the heat, which expands the tissue and it makes it inflamed. We see that in carpal tunnel syndrome. What are some friction-reducing structures? Choose all that apply.
I had trouble with that one.
Anybody have no problem with that one?
Synovial bursa, synovial.
Okay, the bursa, that's one of them. Okay.
Synovial tendon sheet.
And the tendon sheet. So what? This is a bone. So the bone is fine, but it gives us the levers that the muscle attached to that we can then move around, or the levers, I should say. See, if you think you can pronounce it, I just totally sort of did that anyway. And then the skeletal muscles move into the bone. So those are actual tissues that do contract. So those would be the ones that create the heat. So the ones left are these two. So let me show you the slide on that. Does that make sense?
Yes.
So which one
Could you re-explain that part? I didn't really understand what you were saying with that.
Which part, like why do we have these structures, or what I just said before?
Yeah, what you just, like the last part that you just said.
Okay. So the femur is a bone, and the skeletal muscle is a muscle itself. And so the muscle goes into the bones and then moves the bones around.
Oh, okay.
And so when you do that, it creates heat. Like when you do jumping jacks, you get a lot of heat, right? And so, for example, one of the problems with carpal tunnel syndrome is if you do a lot of typing, you move all these fingers around. And all the muscles that go into the fingers and move the fingers around, they are all attached in the forearm. And then their tendons have to go from the forearms, where the meat of the muscle is, through the wrist into the fingers, attached to the fingers around. And so the more you move those muscles, the more heat you create. And then and heat expands, and expansion means inflammation in the body.
Oh, okay, I understand that now.
And so you have some structures that decrease that friction tendency, and the structures that decrease the friction. If you look at this is a tendon. It's like going from the forearm to the fingers. Actually, that goes through the fingers, I think. And then this is a sheet that's around that has on the inside some fluid called synovial fluid. And this is the same type of fluid that we have around joints that we talked when we talked about joints. And
I remember that one.
That was the synovial tendon sheet. That's one of those. And when the tendon moves in and out, that fluid kind of keeps it not from rubbing against another tendon that's right next to it. But it also has a cooling effect, so to speak, in some way. And so it helps not have the friction create the expansion and the heat, or it decreases the heat, it decreases the inflammation. And you have the same thing here. You see this here? This is a bursa. And you have this is the thigh bone, this is the thigh bone, this is the greater trochanter on the outside. And you've got all these bursas overlaying these different muscles. And what that does is when this muscle contracts, it doesn't rub against the muscle underneath. It makes the underneath muscle hot and inflamed.
I know.
Right? So that's a bursa. That's also like a synovial. It's the same thing as this. It's just a bag. It's like a pillow. You think of it as a pillow that cools things down.
Okay, so it's like a cushioning kind of cooling.
Yeah, cushioning, cooling. Yes.
Okay.
Like especially this here on the side of the butt cheek. It's we have the glute muscles there. And I get older patients like 75-ish or so. They often get these inflamed from standing as we get older, you know, and so that they have that's what's called a bursitis. Have you ever had a bursitis, anybody? When one of those is inflamed, it's called a bursitis. I know, it's kind of interesting